I'm hearing some elements of here. It's associated, so it's not totally unlinked to those issues. So we have several delays in a row. Actually, we'll see these sorts of behaviors. So we'll call them higher order delays. Oh, right. Oh. I think this is the wrong. Sorry, folks. I think I opened the wrong lecture here. Sorry. Aging chains is what I want. Sorry about that. Okay. So if we string several of these together in pieces, in a row, in a sequence, we will see higher order delay. So if we string together k of them, we'll see a so-called kth order delay. Now, the thing to keep in mind here is that there'll be differences in behavior coming from both of these. But what we will try to do to kind of be able to compare one with the other, we will imagine a situation where we string these together, we set the parameter such that the overall time to cross across the sequence of delays we put down is kept constant. The difference will be how many delays we have. Instead of just one delay, a first order delay, we'll have two, or we'll have three. But we're kind of trying to keep constant. We're trying to normalize for it. We're trying to sort of have invariant the average time to go from entering the system, this inflow on the left, to this outflow on the right. Okay. So each particular one of these to go across a single stage, the time to go across the single stage will be the mean time to transition across all stages divided by the number of stages. So here we'll have first stage, some time to go across second stage, third stage. And to get the total time across all stages, we could just total those up, it turns out. Okay, they're additive. So here we're going to sort of equalize for how many stages there are and be able to compare the behavior. So this is the behavior of a second order delay. So a first order delay, if we had some input, this is a case where it's starting full and the stock is starting full and then it drains down, we get some exponential decrease in the number of items in the stock. Similarly, we get an exponential decrease in the outflow with a first order delay. With a second order delay, this is what we get. We get the likelihood of still being in the system in one of those delays starting high and going down. But how does this differ from just a single order delay? Yeah, at the beginning, it's sort of rounded here. You're still very, very likely, even after a little bit, to be in there. By contrast, so the sharpest point of the decrease is not until a little bit later. By contrast with the other system, with the first order delay, the sharpest part of the decrease is at first. That's when the gap is the biggest between the outflow and the inflow. The output flow is really large because the stock is really large. Well, there's no inflow, right? Now this is the outflow for that first order delay. At first the outflow is 0, then it rises, and then it falls. The outflow from why is it 0 at first? Why is there no outflow initially? I thought it was starting full. So why is there 0 outflow at first?
Nothing in stage 2 yet.
Nothing in stage 2. It's all in stage 1, so it doesn't come out till a little bit later. Then it starts to come out more and more from stage 2. Why does it drain down like this? Yeah, it has its own outflow. You'll notice that the later part of this reminds you a lot of a what? First order delay, because it's draining stage 2. So you get this kind of build up and then decrease. Here's a third order delay. 3 stages in a row with 3 stages of first order delays. But yeah. This guy, yeah. say this again. This is the outflow from stage 2. The second, the sort of the after the peak, yeah. You're saying, is it kind of like this, or is it like a first order delay? That's a good question. I think this approaches, so early on this is not like a first order delay, but over time I think you get something quite close to a first order delay in terms of its timing, because more and more it's dominated by that second stalk and how quickly that can drain. So I think it is like both, and it's because this guy here, the stalk, is like it becomes like a first order delay later on, okay, in terms of its components. That's the further on you are in time, the more and more likely things are concentrated in the second stalk, and therefore it's draining like a first order delay, that stalk. Does that make sense? Yeah. That's a good question. So this one on the right, upper right, is the outflow. This one down here is, it's this one plus this one. Okay, so it's actually the sum of these two. So it's if we started this at 1 and this at 0, this is the sum of these two. So there was this initial burst at 1. You could think of it as like an impulse coming in. For those who are engineers, you may have heard of a Dirac delta function. There's other names for it too, impulse function. So it's as if you can imagine something came in here. This was 0, and suddenly knocked it up to 1, and now it's draining. It's draining down. Initially, it's all here, but then it drains down so that more and more of it starts to be over here, and some of it's leaving the system, and I'm just totaling up how much is in the system as a whole, either this or that. Does that make sense? With a first order delay, it's just how much is in the stalk, because the rest is gone. Here, it's the sum of these two stalks. With a third order delay, it will be the sum of the 3 stalks, okay? By the way, I'd welcome thoughts on how to present this more clearly. Like you could look at what's the initial value of this. Let's suppose we're interested in getting a graph of stage 2. What is stage 2? What is the value of the stalk of stage 2 look like? If we had to draw it, which of these things would it look like?
More like
It'd be this one. It's just this one times some value, right? Because this is, remember, each of these stages is a first order delay. So this guy here, the outflow from the second stalk, is just the value of the second stalk times some constant. So the value of the second stalk is just very similar to this guy here. Does that make sense? Okay, third order delay. What do you think that looks like? How would you say it looks different?
more widespread.
Okay. More spread out?
Oh, that's the second
Well,
order delay.
this is second order. Yeah.
Okay.
I went back because I'm trying to nudge you, or trying to elicit responses. So what would a third order delay look like? Okay. So narrower. It should start from 0 because it's the outflow from stage 3 in this case, so it should start from 0. And will it be rising as quickly here?
It doesn't start rising.
Because the stuff has to go through stage 2 first, right? And how about here? The likelihood of being in the system still?
It takes longer to decay.
Longer to decay, yeah. So it's kind of more bent here, and here you actually get this kind of, initially it starts and then it accelerates. Okay, now you may think this is a pedantic or sort of, like why are we studying these different order delays? Well, the answer is because system dynamics models are built up out of a small number of pieces. And if you want to capture delays of different sorts, you don't want to have just a first order delay where, input comes in and you get, you have input coming in, you get this sort of response out. If you want to have a response that is more nuanced than that, like maybe it starts slowly and then goes up to something approaching this, so it doesn't just immediately rise. It's something more approaching the kind of what we think of as a delay of this. Then you're going to start to think about building these higher order delays. And in fact, this is extremely common in system dynamics. You have what's called an aging chain. These may be stages of a person's life, because you want to capture the fact that, children can't give birth to a new generation or something like that. So you have children, reproductive age adults, and then older adults who are post-reproductive age. And so you divide the population into categories, or maybe this is age 0 to 4, this is 5 to 9, this is 10 to 14, etc. Okay. So these are different depictions on what you have coming out of the system. You'll notice the first order delay kind of stands out. You get that input to the system immediately, and it starts responding immediately. Others are delayed versions of this, successfully delayed. And you're right, it becomes narrower. As you get larger number of delays, it becomes narrower and narrower, keeping constant how long it takes to get across there. What is it ultimately approaching? Spike. A spike. It's actually, it's a normal distribution, but the normal distribution is in fact becoming narrower over time. So it's approaching the normal distribution, but with the mean of the normal distribution growing. Let's put it this way. The ratio of the height to the width is rising. So these are what are called Erlang distributions, and as k rises, they're approaching a normal distribution, and at a proportional level, the height compared to the width becomes more and more pronounced. So it's becoming more and more exact as terms of sort of how far it's delayed, and it's more and more familiar as to sort of what it means to be sort of delayed here. Here we have a delay that's more and more exact in terms of kind of its the timing in which it takes place. It's not starting prematurely to let things out. Okay. So these aging chains are very, very common. So we have aging chains associated with, say, this is stages of chronic kidney disease, stage 2, stage 3, stage 4, stage 5. Those are clinically known stages, and we can capture them very straightforwardly with these delays. Okay. So it's very straightforward. Just be aware, capture a delay, but you want to do so with more texture than a first order delay. You can string these together, and you'll get out some sort of standard waveforms. Okay, so those were sort of higher order delays here. So